presentations, followed by a discussion of current combustion exascale co-design topics. From her bio, I would like to mention only a few things. She is a distinguished member of technical staff at the Combustion Research Facility at Sandia National Laboratory. She is the founding director of the Center for Exascale Simulation of Combustion and Turbulences, and she received many awards, especially from the DOE Insight Award in 2005, 2007, and 2008 to 2014. Please welcome Jackie J.
Thank you, Horst, for the kind introduction, and to the organizers of ISC for inviting me to give this talk here. As Horst mentioned, I'd like to take the next 40 minutes or so and give you an update on what is feasible in combustion simulation in terms of petascale computing, and then I'd like to present what some of the issues are for moving on to exascale and how we are starting to address some of those challenges in the way of co-design between application scientists, combustion scientists in our case, and with applied mathematicians and computer scientists. So you might be wondering why are we still talking about combustion? Combustion has been around for 100 years, yet our modern society still depends heavily on combustion for our energy needs. And so what we'd like to do with exascale combustion is to be able to predict the behavior of new fuels, both conventional petroleum-based fuels as well as bio-derived fuels, in different combustion environments and the realistic operating conditions at high pressure and at high temperature, intense turbulence conditions. We need to do this in order to develop both the co-design of fuels, so custom fuels optimally tailored to advanced engines that burn efficiently and clean. We need to also do this in order to extend the longevity of our use of fossil fuels and to reduce emissions like particulates from soot and CO2 greenhouse gases. Coming from the US, there are a number of government mandates, both the more immediate CAFE standard of 54 miles per gallon by 2025, as well as an 80% reduction in greenhouse gas emissions by 2050. And so within those kind of short time frames, there may be only opportunity for several design cycles. And so having computation in the mix to augment experimental campaigns is very useful and can shorten the time that these devices can be brought to market. So what I'd like to focus on today are some high-fidelity, first principles, continuum direct numerical simulation methodologies that we've worked on in our group at Sandia and other places. And what we'd like to do is to, with very high chemical fidelity, differentiate the different effects of fuels where there's very strong coupling between the chemistry and the turbulence. There are also, while we're doing a direct simulation where we're resolving all of the fluid mechanical scales from the largest eddy-containing scales all the way down to where we dissipate heat, we still have to impose or incorporate models for the thermochemistry. So we need reduced chemical kinetics models and transport models. In addition, with exascale computing coming online, we can handle a greater degree of complexity in terms of multiphysics, and so we'll begin to start looking at spray combustion, also soot, transporting soot, condensed phase particulates, as well as thermal radiation. A lot of these flows in practical combustors occur in very complicated flow fields, and so we'll also like to look at things like compression of a charge by moving piston, looking at swirl-stabilized flames behind bluff bodies and gas turbines, and even at high-speed scramjet-like flows, which are stabilized, where the flames are stabilized in cavities. So just to say another word or two about what some of these fundamental turbulence chemistry interactions look like, They're motivated by design of advanced internal combustion engines as well as gas turbines for transportation and for power generation. And so this chart on the right, upper right here, shows the local fuel-air equivalence ratio. So richer fuels are moving up this axis, and it's plotted versus temperature. And in this phase plot, you see that the gasoline engines that we typically drive, these spark-ignited engines, operate at fairly high temperature and near stoichiometric conditions. And at those conditions, the engines form a lot of nitric oxide. And with diesel engines or compression ignition engines that you see with the trucks on the road, these tend to operate fuel-rich. And so they sit in this NOx island and nitric oxide island, but also in this particulate sooting island. And so they kind of get hit from both sides. The trend in the automotive community is to go towards low temperature combustion, where you burn at very low temperatures and at lean conditions or diluted conditions, such that you avoid both the soot and the NOx islands. And at these kinds of conditions, dilute, lean, partially premixed, combustion is not terribly well understood. And these regimes tend to occur in mixed modes so that you don't have fuel and air completely not premixed, or where they're completely premixed, but you have something in between. And oftentimes the premixture burns into a reactant mixture that's partially oxidized due to local autoignition occurring. And so there's still a great deal of fundamental knowledge to be learned about combustion in these more extreme conditions where combustion occurs at the ragged edge. And in that regime, there are very strong sensitivities to fuel chemistry. Likewise, in gas turbines, the trend is also to go to very lean conditions, lean premixed here, and for the purpose of getting both high efficiency and low NOx and CO, and also because of the increasing amount of renewables that are coming on the market, especially in Europe. There's a great demand for fuel flexibility and operational flexibility to meet the demands of the fluctuations in the renewables. And so in these conditions, as I mentioned, the flow fields tend to be very complex, and there are also issues with operability, including flame blow-off, flashback, where the flame can flash back up into the premixing section and cause damage, and coupling of the heat release, combustion heat release with noise, sound, and the chamber geometry through thermoacoustics. And so all these effects have to be understood, and predictive models that are used in large eddy simulation that resolves only the energy-containing scales, and in Reynolds average Navier-Stokes, which industry currently use, need these models. One other point is that engine combustion is multi-scale, multi-physics, like many other physics and engineering disciplines. It's a very large range of length and time scales, from the smallest combustor, which is of the order of 10 centimeter diameter, bore diameter in an IC engine, down to very, very small length scales where inception occurs at nanometers. Where a lot of the turbulence chemistry interactions occur is on the microns to centimeters length scale. The chemistry complexity to describe a practical fuel of interest, a hydrocarbon fuel, can require upwards of about 100 species and 1,000 elementary reaction rates in a reduced chemical model. And as I mentioned earlier, there's multi-physics complexity associated with sprays, soot, and thermal radiation, and these are all kind of non-linearly tightly coupled phenomena. So with computing, experimentally, it's extremely difficult, if not impossible in some situations, to stick an experimental probe and get detailed diagnostics in an engine environment, high pressure, high temperature. So a lot of times you can get integrated line of sight types of information and at very coarse resolutions that don't resolve the fine scale physics. So combustion is one of these things where chemistry has to be molecularly mixed before it reacts, and so you really have to, if you want to understand combustion and its impact on efficiency, you really have to understand what happens at the microscale. With computing now at petascale, tens of petascale, and moving towards exascale, we still can't resolve the full range of scales in a DNS sense. And we're fortunate with high performance computing, at the petascale, we can resolve about 4 decades of scales directly. And so you kind of have this opportunity to have a moving window across the range of time and length scales to resolve some of that, but then some of the length scales, but then you're going to have to model some of it, the rest of it. And so the strategy with multi-scale modeling is to go from the quantum scales on up to the device level scales, but use computing, HPC, to help perform DNS in some limited regime of time and spatial scales. And then to develop new parameterizations that help us bootstrap that information upscale to the actual devices. So I'd like to focus your attention then on the continuum regime, where we're going to be looking at mostly at direct numerical simulation and its input in the way of subgrid scale modeling for LES and for RANs. At Sandia, over the last couple of decades, we've developed a DNS code called S3D. This is developed in my research group, and S3D is a compressible reactive Navier-Stokes code. It solves the governing reactive Navier-Stokes total energy species continuity equations using very accurate finite difference methods that are 8th order in space and 4th order in time. And it also treats a range of different fidelities for the chemical models and transport models. And this code has been refactored a number of times for various high-performance computing platforms. Most recently, the code was refactored from MPI to an MPI plus OpenMP version, and then with the help of the Oak Ridge Leadership Class Computing Facility and their readiness program for Titan, it was refactored for a pragma-based approach in OpenACC. I'll talk about that a little bit later. And then most recently, I mean, within the last year or so, through the Co-Design Center ExaCT, some computer scientists led by Alex Aiken and his PhD students refactored the code in an asynchronous dynamic task-based model called Legion, so I'll discuss that as well. But this code now runs as a consequence of these various optimizations on the GPU system, on Titan, and on PISTANK, and various other places. And I think it allows us a little bit of a glimpse of what we might anticipate may be helpful or useful as we move towards exascale. So to perform the kinds of DNS with great detail, it requires a lot of CPU time. And so we've been very fortunate to have this program in the US called the InSight program, which allocates very large amounts of time to open science time at the leadership computing facilities at both Argonne and at Oak Ridge. So most of our computations so far have been performed at Oak Ridge. And with this kind of computing time, I think that at petascale, while we can talk about this multi-scale computational validation approach, so augmenting experiments. At the petascale, we can now perform first principles DNS at ambient to moderate pressures, at moderate Reynolds numbers, that's the ratio of the inertial to viscous forces, and with somewhat complex chemistry routinely of order 40, 50 species that are transported. As we move towards exascale, we anticipate going to much higher pressure, so pressures on the order of 40 to 60 atmospheres, at much higher Reynolds numbers, with much more complex chemistry, describing some of the large hydrocarbon fuels and biofuels with order 100 to 150 transported species, and increasingly complex geometry, handling some of these bluff body, swirling types of flows, cavity-driven flows, and with multiphysics with spray soot radiation. And so this pyramid here kind of describes the DNS validation world, and so currently at petascale, we're looking at DNS in simpler canonical configurations where you can do mini parametric studies, and as we move towards exascale, we can start to make direct comparisons with laboratory scale planes and where we've isolated one phenomenon, and then moving on up into where we've integrated several multi-physics and more realistic system-level types of computations. So these are just icons kind of the kinds of DNS calculations we've been able to perform over the past decade or so with HPC support, looking at a range of fundamental turbulence chemistry interactions from local extinction, autoignition, flame stabilization, flashback types of problems, premixed flame propagation and structure. And I'd like to just show you one example to kind of give you an idea of what's feasible now at the petascale. So this is an example of a lifted flame stabilization that you would see in a diesel engine. So this would be like one diesel jet. And the movie I'd like to show you of a chemiluminescence image obtained from an experiment that Lyle Pickett performed in a diesel liftoff stabilization shows the fuel jet issuing from left to right in this movie, and then downstream at about 40 or 50 millimeters through this chemiluminescence imaging, you see the outline of a lifted flame, and then it occasionally propagates into what looks like popcorn auto-igniting just ahead of it. And so this is a line of sight measurement. The experiments can chart the time series history of the liftoff point, function of time, and the rapid motion, sawtooth-like motion upstream is somewhat indicative that there might be autoignition occurring to help stabilize this flame. But this is about the type of information that you can get from an experiment, and so there's still a lot of missing detail that's not possible to get experimentally. So we wanted to start to shed some light on this microscale detail by performing DNS. And while we can't perform DNS of the full-scale diesel jet flame at the present time, we can look at some of the important features like the liftoff stabilization in a lifted dimethyl ether jet flame. This is an oxygenated alcohol fuel at much more moderate pressures, at 5 atmospheres, which still represent some of the autoignition multi-stage physics that you would see in a real diesel jet plane. And so this is a picture then showing the DNS, stationary lifted DNS of a multi-stage ignition DME jet flame. And let me just play the movie of it so you can get a sense of the dynamicism that's going on inside of this flame. So what you'll see is that turbulent mixing wrinkles this jet, fast-moving jet of DME that's issued into a hot co-flow at 950 Kelvin. So that's the stoichiometric line. On top of that is the yellow surfaces representing the low temperature ignition intermediates, methoxy, methyl peroxy. And then the blue bits represent the high temperature flame that's stabilized on this low temperature ignition. And so you can see that there's an awful lot of structure and transient motion of that lifted flame affected by the turbulence and also by the low temperature ignition upon which it stabilizes. So what we wanted to do with the DNS is to drill in and look at the liftoff branches, the bottom liftoff, the stabilization point. And from some Lambert calculations, we found that there is actually a pentabrachial flame structure at that lifted base, which you could never measure experimentally. And so we wanted to see if that kind of structure persists in this very high intense turbulent sheared environment. So we can look at, because DNS has all kinds of detail, you can look at the detailed physics, and the statistics bear out that in fact you do have a pentabrachial flame by looking at the heat release mixture fraction and the orientation of the flame. You can deduce that there are in fact 5 branches to this flame, which has not been learned, which hasn't been revealed before. Independently, we can also compute a chemical measure of the different structure in this flame. This is called the chemical explosive mode analysis, and involves a calculation, an eigenvalue computation of the local reaction rate Jacobian. And so by doing that, we can identify 5 branches. I turned the flame on its side in case you don't recognize it. But you can see that there's a trailing diffusion flame, a very wrinkled, premixed thin flame structure, and then upstream you see the cool flame, low temperature ignition, and then there's some also cool flame here where the flame is locally extinguished, and then a lean branch, rich branch, and a trailing diffusion flame. Note the red bits, which are the very thin premixed flame structure. So we did verify that, in fact, we have this 5-pronged structure. So what was the upshot of that? The upshot was that that kind of information about the detailed flame structure was then picked up and used by commercial software, CFD by Converge. And through their user-defined function, we implemented this chemical explosive mode analysis detection method of this thin flame premixed flame structure, which enabled them to then adaptively apply more mesh locally in these very thin premixed front structures to help them get better predictions of liftoff stabilization in a real diesel jet plane. And so these are some computations from a large eddy simulation performed at Argonne by Sivendu Sam and his postdoc Pei, and looking at comparisons on the left without adaptive mesh refinement based on SEMA, and on the right with SEMA. So if you can see, before ignition happens, there's very little difference, but then after hot ignition happens, there are some very important differences between refinement and not refining the mesh in terms of the structure and liftoff stabilization and sooting processes in the flame. So it's this kind of information that is being passed on to CFD in terms of better predictions. So where would we like to head as exascale comes online? We'd like to push up in pressure to look at reactivity controlled compression ignition, where we can vary the reactivity and mixing in the engine and tailor it to the fuel to control the ignition phasing with respect to the piston motion, the subsequent burn rate. You don't want to have it burn too rapidly so that you end up with a lot of knock, and also the formation oxidation. So to get there, well, let me back up a second and say that to get there will require a lot more fine scale resolution, so a bigger range of scales, longer simulations, more detailed transporting larger numbers of species, including multi-physics. I didn't talk about staged combustors for gas turbines, but there you have spray as well as thermoacoustics to worry about. And then because I/O won't keep up with compute throughput at the exascale, we're going to also want to include in situ analytics and uncertainty quantification. So let me then switch gears and talk about what we're doing in our co-design center and what some of the exascale issues are. So at the petascale, and up until this point, we've been limited by the peak clock frequency, and flops has been the single biggest cost that we optimize for compute. We also have a modest level of concurrency, and so far, primarily, we've been relying on MPI plus X as the programming model for locality. So we kind of have uniform costs, more or less, within a node and also communicating across the entire machine. Memory scaling has been somewhat flat, maintained the same byte to flop capacity and bandwidth, and more or less the assumed uniform system performance. So, so moving ahead, the constraints at exascale that we've all heard about is that power is going to be the main design constraint. It's going to cost more to move data a very small distance on a chip than it will be to actually perform a floating point operation. Data movement, therefore, will dominate. It'll be necessary to optimize code to minimize data movement. We'll have very, very large concurrencies since the frequencies are fixed or slightly declining. So we'll need exponential growth in parallelism with billions of cores. And we have to be able to reason about locality, data locality, and also possibly about the topology. And memory scaling is growing faster, or memory scaling is decreasing, and while compute's growing 2 times faster than either capacity or bandwidth. And there are issues, lots of NUMA issues, and looking at issues with global hardware cache coherency. So we'll see heterogeneity just about everywhere, and not only in the software, how our software behaves, but also architecturally, and we'll see all sorts of performance non-uniformities go up. So what does that all mean for scientists and engineers that want to use HPC in the future? So I think that future algorithms, everything in the stack, from the application algorithms to the programming environments, the runtimes, and the hardware need to operate in sync with one another and be able to express data locality, sometimes at the expense of flops, and independence. We have to express massive parallelism, minimize data motion, and reduce synchronization wherever possible, and also be able to detect and address faults. So within our interdisciplinary co-design center, ExaCT, for combustion co-design, our charter was to look at all aspects of combustion simulation, from the formulation of the governing equations, to the basic math algorithms, to the programming environments, even down to the actual hardware characteristics that we could, work with vendors on to enable these combustion simulations and include in that both in situ analytics and some UQ. And through this 5-year project, we were able to interact a lot with the vendors to help define some of the hardware requirements, understand some of the hardware limitations, and with several computer scientists on defining requirements and for programming environments, and with the applied math community on designing locality-aware algorithms, especially for solving large systems of pressure differential equations. And our goal here for combustion is to look at block-structured, both uniform as well as adaptive mesh refinement with embedded in situ UQ. And so combustion really here is a surrogate to a much broader range of multi-physics areas that involve solving large systems of PDEs. So within our co-design center, the approach was to look at, initially was to look at proxy applications and proxy machine models. And then in between that, we had simulation modeling of the architectures. And because it was too difficult, many of these applications are million-line applications, and so trying to reason about sensitivities and so on in those types of full-up production codes is a very difficult thing to do. So with the proxy apps or mini apps or skeletal apps, whatever you want to call it, the idea was to express the essential part of the application for the science, express the pain points for performance, and then hide the rest of the complexity that's not consequential to the performance. Similarly, for the proxy machine models for exascale are a reflection of what the underlying anticipated machine architecture is going to be. And here it's important to look at expressing what's important for performance and again, hiding what's not consequential for performance. And so we iterated back and forth on this a lot with the computer scientists in our co-design center. But at the end of the day, to get the actual realistic compute intensities, we still needed to look at some full applications. The starting point for this co-design effort is 2 codes, S3D, which I've already discussed, and also LMC, which is a block-structured, low Mach number adaptive mesh refinement code that's been developed at Lawrence Berkeley Lab by John Bell. And it also has a lot of the similar physics capabilities that S3D has, in addition to adaptive mesh refinement, which we need as we move up in pressure and where we have greater disparities in scale. And at the exascale, we anticipate that we'll need a new code base to be able to encompass these kinds of capabilities. So first, in the area of algorithms and solvers, the goal here is to develop a higher order compressible and a low Mach AMR solver. And in this activity, we looked at a couple of different topics. We looked at alternative time stepping strategies that were more compute intensive, less communication. We also looked at higher order AMR, iterative linear solvers using multi-grid methods, and looking at improved data distribution methods for laying out the AMR data, which is very dynamic and requires a lot of attention to load balancing, and so on. And then we started to look at incorporation of adjoint sensitivity analysis within the workflow of an AMR solution. So just one word about the algorithmic part. We looked at this new improved time integration method based on spectral deferred corrections. This is basically recast the time evolution as an integral in time and iteratively solves for the resulting spectral collocation system. So it's an iterative approach as opposed to the explicit Runge-Kutta method, which is not. This SDC method offers, I'm number of advantages over explicit RK methods in that it's multi-rate, meaning that different processes can be integrated on their own independent different timescale. So turbulent advection can be integrated on a much slower timescale, and chemistry, which occurs much more quickly, could be subcycled within a time step for advection. And this would enhance the work intensity because of the expense of the chemistry computation, which involves a lot of transcendental function evaluations, and at the same time lessen the communication because you're taking advection steps on much larger time steps. It's also an algorithmically resilient approach because of its iterative nature. So if you have detect silent errors, you can just iterate a couple more steps to get rid of the until you get to convergence. And so this method is now being coupled to AMR and multi-grid in both space and time. And initial measures of metrics show that we get about a 5-fold improvement compared to explicit integration of stiff chemistry on current machines. Another area, so in addition to algorithmic improvements, another significant area of improvement or change is in the way we program the software at the exascale. And so these are just to illustrate the challenges with keeping data locality and thinking about the whole way you program this. Currently, we as engineers and scientists have to write functionally correct application code. That's our job. And we also have to be able to map that code to the resources of the machine, to the processors and to various memory components on the machine. And we also have to extract parallelism out of our codes if we want to get any kind of performance out of it. We need to manage the transfer of data. For example, with the stencil-based computations, we have to do nearest neighbor communication, so we have to do that at low levels to communicate across different nodes in ghost cell regions. And in order to hide some of the latencies on the machine, for example, going back and forth between the GPU and CPU, we have to be able to interleave communication with computation. So latency hiding and task scheduling is another responsibility. And then finally, one size doesn't fit all. So all of there's a lot of data-dependent behavior, and how you code may be different depending on the kind, type, and size of your data. And so at the end of the day, it's no wonder that we go home feeling very frustrated, and as we try to move to exascale. And so the shift in paradigm and separation of concerns that we'd like to see is that we as engineers and scientists still have the responsibility of writing functionally correct code. That's our job, and we also need to map or come up with policies on how to map it to various machine architectures. But the rest of that should be the job of a compiler runtime who understands the data and how to schedule tasks and adjust to the data dependencies and latencies on whatever architecture you want to run this on. So, this might be a pipe dream, but we can try to push down this path as much as we can. And we were very fortunate to have some really smart computer scientists on our ExaCT team. This is Alex Aiken and his students, primarily Mike Bauer and Sean Treichler, who worked in our combustion co-design effort. So they have this Legion programming model, which is it's a data-centric model, captures the structure of the program data, through a separate mapping interface, it decouples the specification of the data from the mapping of the tasks and the data to memory and processors. And it lets you have some flexibility in programming choices at different levels. For example, at the node level, if we wanted to use a tiling approach like TITA, we can do that, or we can let the Legion runtime schedule stencil-based computation. And it's very good at automating the data motion, parallelism, discovery, synchronization, and hiding long latencies. And most of all, it has support for both data as well as task parallelism. And while proxy apps and proxy machine models are great at first cut evaluation of sensitivities, in the end, I think there's no substitution for actually coding up a full production code on something that has some characteristics that you might see at the exascale, so for some of these heterogeneous types of machines. So we did that. We ported S3D over to, with Legion, this new programming model, over to Titan, as well as Pisdane and Keeneland, and we're still working on porting it over to various other machines. So in Legion, you describe the data with logical regions. These are arrays of objects that have no implied layout or location. And they're described by an index space, a set of keys that, for example, this might correspond to the mesh indices in a PDE solve. And the field space denoted by the columns in this table on the right. The rows represent the mesh, the columns represent the different fields. So for example, in combustion, these might be your variables like temperature, species composition, and so on. And what you can do with this logical regions is that you can partition this into subregions. You can partition that hierarchically. So for example, in an AMR mesh, you would have some kind of recursive partitioning. And you can also slice the data by the field. So you don't have to operate on all the fields. You can operate on a portion of them if you wish. And similarly to the tree of regions, the tasks can also spawn off subtasks. So there's a hierarchy in the tasks, Legion tasks. The tasks have to specify which regions or subregions they're going to use. They also have to specify the modes or access modes for these regions, including whether it's a read-only, write, or reduction access. And then the Legion runtime schedules these, with this information, can schedule these tasks on the compute resources. So for example, here we have two tasks, task 1 and 2, that both operate on region R but on disjoint fields. The Legion runtime can recognize once you specify the region use whether there's overlap in the regions or whether they're disjoint data sets, and then therefore might be able to proceed independently. So in this first example, the regions are disjoint. Legion runtime says, okay, you can schedule these and run them concurrently on nodes 0 and node 1. If I change the example so that task 1 accesses the same field B in region R that task 2 accesses, and it does it in a read-write manner, the Legion runtime will recognize and infer the data dependence between the two tasks, and it will schedule an operation or a copy operation and wait for the completion of task 1 and its output, copy it to node 1 before task 2 executes. And so it has this dependence graph that it uses computes dynamically. Separately, Legion has a mapping interface where the application selects where the tasks run and where the regions are placed. For example, here I have 5 tasks. These could be placed on either the CPUs or on the GPUs, and the different logical regions could be placed in different parts of memory on the CPU or on the frame buffer memory for GPU. And mapping is computed dynamically, and in Legion, it decouples the correctness of the mapping from the performance. So you might have initially a poor performing code, but you can optimize it for performance. So the code is about 200,000 lines. The production code of S3D is about 200,000 lines of Fortran. As I mentioned, it's a DNS code using an explicit method of lines approach. There are various versions of the code, Fortran plus MPI, hybrid OpenACC. And I should also point out that Legion, one very important feature is that it interoperates with MPI and for us with Fortran, so that we don't have to move the entire code over to Legion, but we can pick and choose what the most compute-intensive parts of the code and migrate just those parts over to Legion. So the data as it's organized in S3D is large, three-dimensional Cartesian grid cells, where the typical per node subgrid size is about 48 cubed or 64 cube grids. Grids per node, and nearly most of the compute kernels are on a per grid basis. It's embarrassingly data parallel. And for a single iteration of the right-hand side and the explicit RK method could involve hundreds of tasks. So there's an opportunity for a lot of task-level parallelism, in addition to the data parallelism, except that the current version, before we converted it to Legion, is that the compute intensity is pretty low. And then the other feature was that this code has huge working sets per cell involving thousands of temporary variables. And so that places a huge burden on memory access. So the performance limiter in this code is not compute, but rather it's memory bound. So this is what the task parallelism looks like within the Legion S3D code. So this dependence graph of tasks on the bottom shows the right-hand side evaluation of the compressible RK method, and the width of that graph is indicative of the degree of task parallelism that's to be had. And this is representative of the smallest chemical mechanism with the order 9 species, which is about 10 times smaller than the mechanisms that we'd like to be using. And this task graph is replicated across all of the nodes because we also have a data partitioning that's data parallel across the volume. And so this is the kind of dependence graph that Legion provides dynamically. In addition to the task parallelism opportunities, we also had to optimize the compute leaf tasks in order to gain the best usage and performance on the GPUs, for example, on Titan. So this plot on the left here, as 90% of the compute available on Titan is on the GPUs, we wanted to make sure we squeezed as much of the performance out of that as possible. So what this plot here on the left pie chart shows are the various compute kernels and the fraction that they use by task on Titan. And so you can see that we've got this optimized up to about 5% idle time, so 95% performance usage, where the biggest compute leaf tasks are in the evaluation of chemistry at 44%, and on the stencil PDE, so the stencils are about 20%. So in addition to maximizing our use by task on Titan, we also have to optimize each of the leaf kernels' performance. That's where you gain a lot of the performance and improvements overall. And so to look at the handful or so of the most compute-intensive kernels and how they compare with the roofline analysis shown in this black line, you can see that both the chemistry evaluation and the stencil operation are memory bound, and then the departure of each of these baseline the leaf kernels from the roofline is the measure of the performance of these GPU kernels. So overall, we get about 80% performance when we optimize each of these leaf kernels. So the Legion, as a runtime compiler, still doesn't treats the tasks as black boxes. It doesn't care how you write the tasks. But we, as I pointed out, we still have this need for very fast leaf tasks, especially for the compute-intensive chemistry, thermochemistry kernels. And we need these for both GPUs as well as CPUs, and for multiple arbitrary chemical mechanisms, since that quickly blows out to being a lot of different combinations. And so Mike Bauer in ExaCT wrote this DSL chemistry compiler called Singe, and takes as input the standard ASCII text table format for chemistry, transport, and thermodynamics, runs it through this compiler, and emits very fast code for both CPUs as well as GPUs. As I pointed out, one of the big challenges in combustion is that we have very large working sets per grid point. For example, the PRF, primary reference fuel for gasoline with 116 species, needs 1,722 double precision reaction rates for each grid point, where the current GPU register file, for example, on Kepler, only stores 128 per thread. And so you quickly see that there's a problem with the working sets. One naive way to get around this problem is to break up your loops, fission your kernels, but this is limited by memory bandwidth. It's very slow to retrieve and read and write the data back in. And so this is not an optimal way to deal with large working sets. So what Mike did was he leveraged the knowledge of the GPU underlying hardware, and with using a warp specialization, where we know that the GPUs execute warps in streams of 32 wide threads. concurrently, so it's a data parallel unit, but it's not necessary to run all the warps running the same identical computation. In fact, each warp could run a different sub-computation on the same, acting over the same data. And in that way, you could generate code that specializes each warp, generate code at warp granularity. And so then these different warps do different computations, especially for chemistry. You don't need to, all species are not, I'm sorry, all elementary reactions, thousands of these are not involved in all of the species. Each species only involves maybe a handful of, each reaction is only involved in about a handful of different species. So there's a lot of opportunity for task parallelism. And so with this, we can get much better use of the memory on the GPUs while also keeping the processors busy and also fit our large working sets on chip on the GPUs. And so in addition to the performance gains I'll talk about in a minute from that, we also looked at in situ chemical explosive mode analysis and moving this eigenvalue solve into the S3D solution to steer mesh refinement. And this is a tedious task if you're going to do this manually, because you would have to interleave the computation across the different Runge-Kutta stages, and it would in a way that doesn't impact the critical operations. So it'd be very hard to schedule manually, but we were able to schedule this eigenvalue solve with the Legion code in about a day's time. And so it speaks really highly to using these asynchronous task execution models, not only for your solve, but also for your entire workflow, as were a lot of the analytics that you could move in situ. And so this is just an example of the Legion execution as given by the profiler on a Titan node, including the in situ schema and analytics. These are different runtime utility processors that compute the task dependence graph dynamically. These are the Interlagos CPU processors. There's 8 of these that we were running on. The orange bits, these different colors are the different types of tasks. The orange bits are the SEMA analytics that were using the spare cycles, whereas most of the computation was performed on the Kepler processor. And so let me just say a quick word about the performance. The Singe DSL was about 3.75 times faster than previously hand-tuned data parallel CUDA kernels. And then we had 3 test beds, Keeneland, Titan, and Pisdane, with varying numbers of types of processors, different numbers and types of GPUs, and different types of interconnects. And so this is a weak scaling plot showing the throughput scaling on Titan. And so we've scaled Legion out to, I think now, about 13,000 nodes. This slide doesn't reflect it, and we're working on scaling it up to the full machine. And so increased throughput is good, so higher up is better. Flat line shows good performance with scalability. So the baseline MPI only code is shown in green. The red line here shows the production OpenACC code with MPI plus the directives. And then this Legion, I would say call it a pseudo-experimental / barely production mode code, is using the GPU mapping. This is mapped onto the GPU only with Legion. And so you see we got about a 2.25 to 2.5x speed up from OpenACC over the MPI only code, and an additional 1.5 to almost 3x speed up using Legion. And so we just compared the Legion code with the MPI only code. At one node, we got a 4x speed up, and at larger core counts above 8,000, there was actually an increase of over 7x, and that improved the greater speed up at larger core counts, we believe, is due to the asynchronous dynamic task scheduling, which is able to overcome the network latencies at larger core counts, which the MPI only code is not able to do. So, and then finally, if we look at the SEMA performance numbers, this is including the in situ analytics, both on Pisdane and these 2 left plots, with the MPI only Fortran code compared with the Legion code. It took about half a second out of 7-some seconds to do to compute the eigenvalue solve, whereas it only took about 0.01 seconds which in the Legion version. So you've basically got the analytics for free. Not quite as good improvements on Titan, but still very substantial. So 98% reduction in cost with Legion on Pisdane, 84% reduction in cost on Titan. And so just to conclude, I'm going to skip these. This is not, that's why I say it's not quite research, production code. We're actually doing production runs with this code now on Titan and able to run end-of-decade auto ignition runs at high pressure, 25 bar, as a result of this enormous speed up. In this particular case, for the production run, we were seeing about a 5x speed up. And so lessons learned, there's a lot of potential, I think, with these data-centric task-based models, and including not just the solve, but also the in-situ analytics. The code is just easier to modify and maintain. You can porting the code is just developing a new mapper. It's easy to tune for performance. New functionality as you build up your workflow just means adding new tasks. And the Legion runtime realm will just help you figure out the dependencies and scheduling. I have to put a caveat there, though, to say that in our experience with modifying this code, there still is room for improved productivity. And I think there's a lot of room for developing higher level abstraction layers for scientists and engineers to write to, rather than writing it at very low levels. And so that's perhaps an area that we can work on in the future. But co-design has been a great experience with working closely between computer and computational scientists, and I think that's the only way to go if we're going to actually get applications to really run well on exascale machines.